Hi and welcome to my video series on vectors and lines. This is from Unit 3, Topic 2 of the Specialist Math curriculum. And I'll be talking about a few things. There's quite a bit of definitions in this work, and I'll break this down into quite a few videos. I'm not quite sure yet how many. This is what I'm working on, some learning goals, success criteria, but worth pausing and having a read through these. And of course, some textbook references for the Cambridge text that we're currently using. So let's talk about vectors and lines. So let's start by considering a linear function. Just going back in time a little bit. How many coordinates are required to fully describe a unique linear function? And I hope that you recall that as long as we have two coordinates, there's only one unique linear function that can pass through those two coordinates. And so the answer to that is 2. So if a vector is given to us as OA, which is position AB, this describes the location of a coordinate AB, and it describes in itself a vector, a straight line segment, this one just here. But more importantly, if we had two vectors, A and B, so those two position vectors starting from the origin, well, A and B themselves describe a line which I'm calling L1. And so if we know two vectors, that describes a line. And it's really important to recognize that we might know nothing about L1, but if we have those two position vectors, there's only one line that can go through A and B there. L1 is called a line. It goes on infinitely in both directions, and that's how we define a line. A vector has very specific endpoints, so it's definitely worth noting that difference as well. This is the more important formation though. So we can define P, which is a position on a line, where we've got L1. We're trying to define L1. And this is a different way of defining a line, which actually falls closer to our usual gradient intercept sort of form. So let's just say we're trying to define the position along line L1. And we start by saying we know a point A, so position A. And that point will be what we call our initial condition. So at t equals 0, time equals 0 in that sort of motion context, but lambda and mu come up a lot in this as well. So let's say we have point A there, and if OA is equal to the vector A, then we call the vector A our initial position vector. Now let's say we place another position P. This is a general point now. So A is a very specific point that we've chosen. P is a roaming point. It's a moving point. And P is always on L1. And we just want some way of describing every point that P could be. So what we do is, because we don't know RT, and this little RT here, this is our vector that describes every point P could be on that line from the origin, from position O. Because we don't know RT, but we do know A, we consider, well, what else might be handy? And the other thing that might be handy here is a vector that is perpendicular to L1. So we're going to go out looking for that vector that's perpendicular to L1, and we're going to call that vector D. And so D is the vector that's parallel to the line, and D can be any length. So in this case, I've got D, and I've kind of denoted that D is it's kind of like the unit vector that's parallel. But you know what? It's not commonly actually a unit vector, and we don't specifically aim to use a unit vector. So D could just be any vector. In actual fact, if we have a second value on the line, D is often the distance between A and P. So it's that simple. But we do know that this forms a triangulation of vectors, and if we want to know RT, which is a position vector on L1, well, it's just A plus D. And of course, because the position is moving along L1, it might not just be A plus D, it might be A plus 2D, which would take us maybe to here. Or it might be A plus half a D, which would take us to here. Or A minus half a D, which takes us down here. Either way, our position is always on L1 because vector A takes us from O to the line at a specific point, capital A. And then D, because it's parallel to L1, just continues to take us to different points on the line. So this works well. And so what we write is RT here is the position on line L1, which is represented as A plus TD. Now I've got some stuff in green here which you're welcome to have a read, but in short it's just this recognition that RT equals A plus TD is kind of the vector linear function, where A is like our y-intercept, but it's our initial position, and D is like our gradient, except D is kind of more of a direction thing in this context. T is like our x. T's that, we vary T to find different positions on that line, and RT is like our y. It's a function in terms of T. So it really links quite nicely, but it is a little bit more complex. It's important to note here that D can also sometimes just be B minus A, the difference between 2 points on the line. And that B minus A vector is, of course, the vector or a vector that's parallel to L1. So it can be B minus A, but to be honest, in most cases it's represented as D in the general sense. So you'll see that come up a lot. So let's carry on and have a look at a couple of examples. We've just got 3 to look at now. So in example 1, I'm asking if the vector equation of a line L1 is known to be this. So I've given you a vector equation. I'm representing it as that sort of matrix vectors or the column vectors there. Determine the equation of the line in y equals mx plus c. So what we have to do first of all is just recognize that we've got this A, which equals 5, 0. And remember that A, that was kind of our initial value. And this is kind of the coordinate 5, 0. So when x is 5, y is 0 is an initial value there. But we've also got D is equal to 1, -2, which tells us our direction, which is our variance here, is when x equals 1, y equals -2. In terms of a gradient though, that's telling us that if we go along 1, we go down 2. This is actually a gradient of specifically -2. So you can see the connection there. And better yet, if you're in any way unsure, bring this out and plot this line. It starts at, I'll say that, sorry, that's not right. Starts at 5, 0, which is here, and then it moves along when t equals 1, it moves along 1 down 2. And when t is 2, it moves along 2 and down 4. And we can see our straight line forming right there. As t is negative, it moves up in that direction. As t is positive, it moves in that direction. So in the form y equals mx plus c, it's important to note here that we already know the m, we just don't know the c. But that's pretty easy to determine. So the m comes from d, and the m is kind of like the y component of d divided by the x component of d, which is the -2 divided by the 1 in this case. So it's a fairly simple case. So we get y equals -2x plus c. And we also know that at x equals 5, y equals 0. So we can use that knowledge to our advantage and recognize that this means 0 equals -2 times 5 plus c. So of course c equals 10 and y is equal to -2x plus 10, which can be rearranged in a couple of different ways depending on what's being asked for. So that's our the equation of that line. But the vector form of it is a little bit more robust as we move into 3 dimensions. That's why we're mucking around with it in 2 dimensions now, but as we move into 3 dimensions, it becomes important. Now let's determine another vector equation of this line. So it's important to recognize here a couple of things as well. We've got our gradient or direction here of 1, -2, and we've got our starting value. Now this line here, the one I'm looking at over the side here, it never changes direction. What doesn't matter as much is actually our starting value. So it turns out that we could use any number of starting values. In fact, there's an infinite number of them. There's one here, there's one here, there's one here, there's one here, there's one here. So there's plenty of starting values we could use. I know that I moved the long one from 5 to 6, and I moved down 2. That was 6, -2. So I could use that position. Or I could use 7, -4. Or that's my y-intercept plus 10. So I could use 0, 10. And each of those yield a new separate vector form or vector equation of this line. So I have got, not y anymore, I've got RT, which is a vector, is equal to A plus TD my d stays the same. So I've got t times 1, negative 2. That doesn't change. But a could be anything. A could be 0, 10. Or a could be 6, negative 2. So I wasn't really accurate there. A couldn't be everything or anything. But it can be a lot of things that follow this specific rule of existing on that line. So yep, there's lots of plenty of different vector equations available. Let's have a look at example 2. The vector equation of the line r lambda is 106 plus lambda 331. Lambda comes up actually more than t. T is a bit of a problem because it can be confused easily with motion, and this can be used in motion sense, but it's not always used in a motion sense. So if the vector p equals 6i plus aj plus bk lies on the line, determine the values of a and b. So it's important to recognise here that r lambda, you have to forgive my drawing of lambda, can be written in ijk form, as p has been, that position vector there. And that can be written as 1i plus 0j plus 6k plus lambda 3i plus 3j plus 1k. Now I don't need the zeros and ones there, and in fact I can get rid of that 0j completely, but I need you to recognise here that this produces a situation where we can equate i's, j's and k's. And lambda just gives us a particular position, and p is that position in this case. So I get 1 plus 3 lambda I. And that of course has come from that term and that term. And then I get 0j there, so I've just got 3 lambda j, and then I've got 6 plus 1 lambda k. So there's my 3 points on that position vector, and I can now equate each of those. So I get 1 plus 3 lambda is equal to this value here. So let me just go that. Oh, that's not what I want. This value has to be equal to 6, and this value has to be equal to the a, and it's going to be quite dark. This value has to be equal to the b. So I've got some known quantities here which I can use. So 1 plus 3 lambda is equal to 6. I can actually solve for lambda in this case. 3 lambda is equal to 5, and lambda is therefore equal to 5 on 3. And that means that a is equal to 3 lambda, which equals 5, and b is equal to 6 plus lambda, which is equal to 7 2/3, and I've solved for a and b. And that point will now lie on that vector equation of a line. Example 3. Determine the vector equation of a line segment that joins A 5, 1 and B 11, 2. Okay, so I've just quickly drawn a diagram, and here's my positions A and B, very rough diagram at that. This is a line segment. You'll notice that the line segment terminates. It has endpoints. So it's not a line, it's a line segment. You could describe the line, but I'm going to describe this line segment and show you how we can use a restricted domain to set this up. What's important here though is to recognize that we can easily define a starting value and easily define a gradient for a question like this. So first of all, we can define OA as the vector from the 0 position out to A, and we can define OB as the vector from the 0 position out to B. Now what I'm going to say is let's let A, our initial position, just be OA. So we've got a starting position, and then therefore B is our ending position. So what I can do is determine D, and you recall earlier that D could be written as B minus A. And so that was doing that straight subtraction there. So I'm going to do that as B minus A as well. It has a nice little result which I'll show you in a second. 11, 2 minus 5, 1. And so that means that my D value is going to be 6, 1. So that represents a gradient. Now, it doesn't represent a gradient of 6, it actually represents a gradient of 1/6. If I move along x6, I move only 1 up, so it's a 6 per x unit. And of course, this leads me to the fact that OP where P is just some position on that line segment, is equal to, let's start at A, and let's just move along some value T along my direction vector. And that, of course, is equal to 5, 1, my starting point, plus T along my direction vector. Now, you don't always have to go this way, but if T is 0, I'm at A, and if T is 1, I'm at B. And if T is between 0 and 1, I'm somewhere between A and B. But if T is negative, I'm on the line that connects A and B, but I'm before point A, so I'm somewhere here. And if T is greater than 1, I'm beyond point B. So actually, I can restrict this domain and say, for all T that's greater than or equal to 0, less than or equal to 1. Just be careful that A and B are also included points. And by restricting that domain, I'm now indicating every point P for every, so T is a real number, and there's an infinite number of real numbers between 0 and 1, so every point P between A and B on that straight line is represented by that vector. So there you have it, that's our first video. It's a bit of an introduction, lots of definitions in there. Watch it again if you need to, or ask questions as you require, but it does cover some of the basis. But for me, probably the biggest takeaway is that recognizing that we're dealing with a situation that's very much like linear functions, but in vector form. And this is only, all it's doing is describing a point on the line segment between A and B, or generally on the line L1. All the best.